Far out in a remote part of the Sahara Desert, there's a mystery. Scattered around in the sand are thousands of chunks of strange yellow-green glass.
It is really a mysterious glass, and we scientists are still kind of puzzled how these things formed.
The ancient Egyptians knew of this extraordinary place, but for thousands of years, it's remained unexplained. Now, a group of scientists plans to finally solve this mystery. It will take them on a journey from the depths of the desert to the Cairo Museum and the test site of the world's first atomic bomb. And what they reveal may pose an unsuspected threat to us all.
What I want to emphasize is that it's hugely bigger in energy than the atomic test, 10,000 times more powerful.
Heading for the great sand sea of the Egyptian Sahara Desert, a team of scientists is on a mission. Their aim? To discover why tons of a most unusual glass are lying in the middle of the desert. One of the scientists, American physicist Mark Boslow, thinks he may at last have come up with the answer.
It's a scientific mystery because it's unique. We don't know exactly what the process was that caused the creation of the glass. We know it's a natural phenomenon, and therefore it requires a natural explanation. It may be a very unusual event, but it's certainly not a mystery that can't be solved.
Working with colleagues, Boslow has developed a dramatic new theory to explain how the mysterious glass was produced. He has a terrifying vision of what happened here. Now, for the first time, Boslow is in the desert to see the site for himself. He is hoping to find the final pieces of evidence to complete his theory.
I've been reading about this place for the last 20 years. There's only so much time you can spend sitting behind a computer looking at tables of numbers. That gives you a good quantitative idea, but it doesn't really give you intuition. To develop that intuition, I really think it's important to go out in the field and have a look.
Joining him are geologist Ali Barakat and geochemist Christian Kerbel, who, like Barakat, is an old desert hand. They have spent years studying the mysterious event which must have taken place in the desert.
We scientists have been interested in these desert glasses for a very long time because they are very different from any other natural glass that we know. It's just such a mysterious glass.
Yes,
Barakat is Egypt's desert glass expert and has traveled to the area several times.
You must go to the south and go to the north. I know the area like my finger.
Barakat's interest dates back to 1998 and a remarkable discovery he was involved in. It took place in the Egyptian Museum in Cairo. Hidden away in a dark corner of the Tutankhamun exhibition was a necklace made of different colored gems. At its center was an intriguing yellow-green carved scarab. It was said to be chalcedony, a semi-precious stone. But mineralogists were not so sure. Surrounded by armed guards and officials, Barakat and his colleague, Vincenzo de Micheli, were allowed to examine and test the jewel. And the tests revealed that the scarab was not a semi-precious stone. In fact, it was made of glass. But it was not a glass like any other produced by the ancient Egyptians. Barakat had an idea where the glass came from. He knew of a 10th century Arabic book with a map inside, which showed the location of a large mineral deposit in the Egyptian Sahara Desert.
And on the map, he describes the Mediterranean Sea in the north and the Red Sea to the east, and the Nile River, and the pyramid.
And far out in the desert, the book describes a mineral it calls peridot. Peridot is a greenish-yellow gem, but Barakat had never heard of peridot being found in this part of the desert.
I am very happy because I found this passage and this book, because he recorded for the first time the strange material.
Barakat guessed that the Arabs had discovered the source of the glass in Tutankhamun's necklace. What's more, he thought he had seen some pieces of the same glass. In the Geology Museum where he worked, there were samples of glass brought back from this part of the Sahara by an English explorer. In 1932, Patrick Clayton reported that far out in the desert, he had discovered chunks of glass scattered over thousands of square kilometers of desert. He had no idea how it had got there, but he brought back some samples. Since the discovery of Tutankhamun's jewel, several scientific teams have traveled into the Sahara to try to find answers to explain the origin of this unusual glass. Barakat and his team are the latest to make the journey out to the glass area. It's a long, hard journey through the desert. It will take them at least 3 days driving and 3 freezing nights before they can even start looking for any glass. Over the years, scientists have been struggling to find an explanation for how this unusual natural glass ended up in such a huge area of the Sahara.
Compared to some of the other glasses that we have in nature, these are really interesting because they are clear. They have a color and this pure silica composition that makes them really unique in the world. We know no other natural glasses that look like this or have a composition like this. And so we scientists are still kind of puzzled how these things formed.
The puzzle for the scientists is that the desert glass is not like any other natural glass found on Earth. Most natural glass is volcanic in origin. Volcanic glass forms when hot, molten magma solidifies rapidly, usually when it meets cold water. Volcanic glass is relatively common, but its chemical composition and dark color are quite unlike the desert glass. Over the years, there have been a few bizarre theories trying to explain what it's doing in the desert. One idea suggests this area was once swampy, and that the glass was left behind as sediment when the swamp dried up. A key aspect of this theory is that the glass forms slowly at low temperatures. But Christian Kerbel had some doubts.
When I first heard about this idea, I thought, well, it's an interesting one, that it forms at low temperature. But I wasn't quite convinced that the desert glass really formed this way. I thought, well, maybe there is a way we can find out if it formed in a high temperature or if it formed in a low temperature.
Kerbel turned for help to the Natural History Museum in Vienna, whom he's worked closely with in the past. Using their electron microscope, he searched the desert glass for a mineral called zircon. Zircon is remarkably stable, but starts to break down at high temperatures. Kerbel looked for zircon crystals that had begun to disintegrate.
And what this tells me is that the glass formed at a very short time and a high temperature. And to understand exactly which temperature we're looking at here, I need to analyze the different bits inside here.
As the zircon disintegrates, it forms light and dark patches. In the dark patches, the zircon has broken down into a form of silica. The amount of zircon left in these areas shows how far the disintegration has progressed and indicates the temperatures reached.
In the darker areas, we have less zircon and more silica. And what this tells us is that this little zircon crystal has decomposed partly because of the high temperature, but not completely. And the ratio of the two elements tells me that the temperature was about 1,800 degrees Celsius.
1,800 degrees Celsius is hot, incredibly hot. Volcanic lava is only about 1,100 degrees Celsius. Whatever happened here in the desert, the heat required to produce the glass was phenomenal. What Kerbel found convinced him and everybody else that they had to look for another explanation. There was only one thing they knew of that could create such a staggeringly high temperature that it melted the ground. A meteorite impacting with Earth.
So there's a lot of material that falls on the Earth from outer space. Tons and tons of this material falls on the Earth every day. And most of them are very small, just like dust. Some of them are pebbles, and they make shooting stars in the atmosphere. And sometimes a really big meteorite hits the ground at very, very high speed. It melts the ground, it vaporizes the ground, and these high temperatures and pressures are enough to melt a huge quantity of rock.
If the molten rock formed by a meteorite impact cools rapidly, it can turn into glass.
There are, for example, these glasses here, they're called tektites, and they are thrown away from impact by hundreds and even thousands of kilometers from the crater. But these glasses are very different in appearance and shape and size from the desert glass that we have here.
Kerbel is a world expert on meteorites. And even though the desert glass is so different from ordinary meteoritic glass, he is convinced it must have been formed by a meteorite. He hopes to find evidence of a massive meteorite impact in the desert. They still have one more day of driving before they can even start looking for any glass or any signs of what occurred. They are now in the heart of the Great Sand Sea. It's one of the most arid, inhospitable places on Earth. No one can live here. It can be 10 to 20 years between rainfalls. Extreme conditions even for the Sahara.
If we go a little further down,
we are here.
And on this one here,
we are here, and then the glass area is all this area. We'll camp at the end of the rocks and the sand here.
Right.
Like that, we'll make the camp sort of in the middle of the high concentration of the big glass.
Just one.
Yeah,
This
25
this
or
one,
5.
not this.
Summer temperatures can soar to well over 50 degrees Celsius. There are no roads, no tracks. The massive parallel sand dunes stretch for hundreds of kilometers north-south. Each dune is a challenge, and without highly skilled drivers, the cars could easily overturn as they slide down the soft sand. At last, they are approaching the area where the glass is found. One of the mysteries about the glass is that it's scattered over an area as big as Devon.
The site to me looks like Mars. I don't think there's any place on Earth that's this desolate, certainly no place I've ever been.
The glass is not thick on the ground, but pieces can be found scattered between the dunes.
I'd seen pictures of the glass before, but the first time I reached down and picked up a piece and held it up to the sun, it was very exciting.
No one knows how much glass is in the desert. Estimates range from hundreds to thousands of tons.
oh, here's a piece. Oh, look at this. There's a nice one. And another one. So this is an area, and look down here on the ground. You can actually see it. If you look here, you see the nice pieces lying around here. There is a piece here. There's a piece there. There's a piece over there.
Most of the glass lying on the surface is small and rounded, sandblasted and polished by the sand and the wind. Other pieces are buried in the sand and are much larger and rougher.
This one here is mostly pitted and dull because it has been sitting underground, and only the nice, smooth, shiny part was exposed to the sand. And underground, it has been etched by water over hundreds or even thousands of years.
New pieces of glass can always be found, as the huge sand dunes are constantly shifting with the wind, moving at a staggering 10 meters a year.
It's interesting. Every time you come here, you find different glass.
There's certainly glass under the dunes.
There's certainly glass under the dunes.
As these dunes move, they reveal more glass.
Exposed, indeed, yeah. So it's a very beautiful area, too.
Yeah.
Although there are no obvious signs of meteorite impact, Barakat thinks there is some evidence, not in the glass, but in the rocks. On a previous trip, he found an unusual little black rock.
I collected it by chance. I found it by chance. I was looking for glass, and I found this strange, shiny black material. So it seems strange for me. So I carried to Cairo and did some tests.
And tests in Cairo revealed that tiny, shiny particles in the rock were diamonds. Similar diamonds have been found elsewhere where meteorites have landed, created by the high temperatures and pressures during the impact. Barakat is now searching for more signs of an impact in the sandstone rocks in the area. A large meteorite smashing into the ground leaves behind other clues. Under the microscope, the tiny grains of quartz, which this sandstone is mostly made of, are usually clear inside. But Barakat and others have found samples where some of the quartz grains have distinctive lines caused by shock waves from an impact. This seems to provide more support for a meteorite impact here in the Sahara Desert. But it doesn't explain why the glass is so different from other meteoritic glass. The team can't agree about the significance of this evidence.
I'm really interested in the distribution of the shocked quartz relative to the glass.
Right.
Seems like the glass covers an area of hundreds of square kilometers, but it seems like the observation of shocked quartz is only in one spot.
Right, yeah. Well, I'm not sure that we know for sure yet where the shocked quartz is. There are a few spots that have been surveyed so far and needs to be confirmed. You see any glass?
But Kerbel thinks he has made a discovery, which leaves no doubt as to the origin of the glass.
I see
But I
the
think
bedding.
this sandstone is broken up.
Most of the glass is completely clear, but a few pieces are not.
There's a nice little
The
piece.
ones that show clear, white, and black all in one piece.
The pieces of glass with black streaks of material inside are key to Kerbel's discovery. To establish what the material trapped in the glass was made of, Kerbel examined it in his lab in Vienna. He analyzed it by bombarding the black bits of the glass with neutrons, and after weeks of measurements found small traces of the exotic element iridium.
Here are the peaks that indicate the presence of the element iridium, and this is something we would not expect to find in rocks on the surface of the Earth, and this is characteristic for meteorites. So here we have very good evidence that a meteorite really hit the Earth and was incorporated with the glass when it formed.
Finding iridium is good but not conclusive evidence of a meteorite impact. After over a year of searching, Kerbel found another rare element, osmium.
The results are absolutely exciting. We see that the abundance of the element osmium is about 50 to 100 times higher than what we would ever find on the surface of the Earth. And more importantly, the ratios of the isotopes of osmium are very different from surface rocks of the Earth. They are clearly extraterrestrial and show that a meteorite hit the surface of the Earth in the sand when the desert class formed. So we have a eureka moment here. We now know there was a meteorite impact.
Kerbel is now totally convinced that a meteorite was involved in forming the glass. But there was an obvious problem with the meteorite theory. Perhaps the biggest problem of all. A meteorite impact leaves behind a crater, and no one has ever found any trace of a crater in the area where the glass is found. For Kerbel, the lack of a crater doesn't create a problem. He has an easy answer.
I think what we're looking at is probably a very deeply eroded structure. A fresh young crater looks maybe like this, and it is filled in here with broken bits of rock and melt and so on. But with time, all this disappears, and all that we might have left is this central area here, which is very difficult to detect.
A meteorite large enough to scorch and melt such a vast area of ground had to be big. And even if the crater's been eroded, there is still one place from where it should be possible to spot it.
Booster ignition and liftoff.
Farouk Elbaz is head of the lab in Boston that interprets pictures of Earth taken by orbiting satellites. He's been looking at pictures from space since the 1960s. Back then, only about 20 impact craters had been found.
With the advent of satellite images from space and the fact that we're going to be recognizing all of these circular features, we now have at least 200 that are proven or semi-proven impact craters.
One reason there are not more known impact craters on Earth is that some are so big they can only be spotted from space. And the older they are, the harder they are to find.
It is really important to look for a crater that has the right age for the formation of this glass, because if we say that this glass is of meteorite origin, which is most likely, then there should be a crater of that age that would have formed that glass. So these things must come together.
To help Elbaz in his search, he needs to know the age when the glass was formed. And it is possible to pinpoint the age. One technique is based on the rate at which the element uranium decays. It leaves tiny scratch marks on the glass, which, when counted, gives its age. This method produced a date for the desert glass. It was formed nearly 30 million years ago. It was an important result. But could they find a 30-million-year-old crater?
It's not really a problem in this part of the world to locate a 20 to 30 million year old structure, because no matter what the erosive processes were like, you still have in the subsurface the imprint of that impact. For instance, we have the structure here in Chad that has been dated to be older than 200 million years, which means that anything that is 20 or 30 million years would certainly be visible.
So Elbaz and his team have been searching the area looking for suitable candidates.
We have some craters in here, a tiny one in here, larger craters in south of here, but nothing in that zone that can be called an impact crater. So here is the Great Sand Sea and the dunes going down southward this way. And the silica glass region is right here, and it is a little too far from any of the impact craters that we have formed around. So we conclude from that we have not really found the smoking gun for the silica glass in the Western Desert in Egypt.
Whilst studying the satellite images, Elbaz spotted a circular formation that he thinks needs closer inspection. But the formation is 100 kilometers from the main concentration of glass, and other scientists remain doubtful that this could be the source. Yet, if there's no crater, then some enormously powerful cosmic event happened here nearly 30 million years ago, and left little more than glass behind. It's this seemingly impossible puzzle which could be solved by the new theory Mark Boslow is developing. The theory starts with an observation made 60 years ago in the desert of New Mexico. The Trinity site is where the world's first atomic bomb was detonated. Sergeant Ben Benjamin was part of the official photographic team. He was just 22. Cameras were set up at several locations. Ben Benjamin was in a concrete bunker 6 miles from the blast site. For all of them, it was an awesome, almost surreal experience. At 5:29 on the morning of July the 16th, 1945, the bomb was exploded.
We had a PA system. They were counting down in seconds, and when it came to -10, I switched on all 4 cameras, and it went off, and it was incredibly bright. It turned out to be 20-some times the brightness of noonday sun. And my God, it was the most amazing thing that I had ever seen in my life, and I'll never forget it.
A mushroom cloud exploded into the sky with the force of 20,000 tons of TNT. A week after the explosion, Benjamin was allowed into Ground Zero. What he saw was startling.
And of course the whole tower that the device was on, all that steel, tons and tons of steel, was absolutely vaporized.
And a bigger surprise was what had happened to the ground.
It was covered with green glass, the melted sand here. All the sand had melted on the top, the first quarter inch or so. This green glass was covering the whole entire area, and it was cracked, and but one could walk on it, and you'd crunch. It'd be walking like on a field of maybe ice.
The sand was transformed into a thin layer of glass, covering an area nearly 600 meters across. Could something similar have happened in the Egyptian desert, but on an even bigger scale? The area where the desert glass is found is huge.
From here we go down another about 10 or 15 kilometers and we find still some glass, and we go up about another 30 kilometers even and we find glass. We're very close to the center of the area where we have the glass around here.
If such a large area of glass was formed as a result of an explosion, it must have had the power of many thousands of atomic blasts. A natural explosion of that magnitude was completely unheard of. No one had any idea of how such a devastating blast could have been produced. The only clue came from a place called Tunguska in the forests of Siberia. In 1927, a Russian scientific expedition visited Tunguska to investigate a massive explosion. The explosion had actually occurred in 1908, but Tunguska is so remote it was nearly 20 years before they saw the scale of the devastation. They were astounded. More than 80 million trees had been destroyed. The scientists were puzzled. What could have caused such an enormous explosion? Their first thought was that it was a meteorite, but they couldn't find a crater. They returned to their laboratory and carried out a series of slightly odd experiments. No one had seen anything like this before, and Tunguska became a scientific mystery. Since then, scientists have had many theories, but it's now assumed that an extraterrestrial object somehow exploded about 8 kilometers up in the atmosphere. This aerial burst was equivalent to about 20 million tons of TNT. Perhaps a similar aerial burst, but even bigger, happened in Egypt. What happened there was hot enough to melt the ground over thousands of square kilometers. This is where Boslow's expertise comes into the story. At the Sandia Labs in New Mexico, he's developing a computer model to see if the airburst theory can be right. An event in 1994 was the turning point, the impact of the comet Shoemaker-Levy with the planet Jupiter. When the comet went into orbit around Jupiter, it broke up into over 20 fragments. Then, one by one, these fragments hurtled down into the Jovian atmosphere. Nothing similar had ever been witnessed.
I think that the impact on Jupiter was really one of the most exciting things to ever happen in the history of science.
Boslow's speciality is the physics of large impacts, and for that he uses computer simulations. For Boslow, the Shoemaker-Levy comet was to be the biggest, most exciting experiment imaginable.
This was a real opportunity to see something that we couldn't see in the laboratory. Something of a scale, of a magnitude way beyond anything imaginable, beyond our wildest dreams.
Boslow's team had been developing a new theory which predicted that the impact would produce a massive fireball.
This is a sequence of snapshots from our simulations. The top image shows this incandescent fireball rising over Jupiter's horizon to be seen from Earth. And in subsequent frames, you see this fireball growing and cooling, but growing into this enormous plume to very high altitudes. It just gets huge.
When the fragments of Shoemaker-Levy smashed into Jupiter, the pictures from the Hubble telescope were just as spectacular as the simulation predicted.
When we saw the Hubble Space Telescope images for the first time, we were so excited to see this spectacular plume rising over the horizon.
Their predictions were very close.
These are actual observations, snapshots from the orbiting Hubble Space Telescope. In the first image, you see this incandescent fireball rising over the horizon, and in subsequent images, you see it growing into a plume, and it continues to grow to this enormous size.
This massive plume of hot gas they predicted was ejected well over 3,000 kilometers out into space.
It was a spectacular explosion. I mean, it was just a tremendously enormous explosion beyond anything anybody's ever experienced in the solar system.
The Shoemaker-Levy impact on Jupiter was a pivotal moment in science. It made scientists rethink what could happen here on Earth.
So this really was a turning point in my understanding about how impacts work. I and most people thought of impacts on Earth as events that create craters, collisions with the solid Earth, and typically we ignore the atmosphere. We ignore atmospheric effects. Well, the atmosphere is tremendously important, and this is the lesson we learned from this.
The Shoemaker-Levy explosion had been observed with interest by another scientist too, John Wasson, one of the world's top meteorite experts. He had also been puzzling about the origin of Egyptian desert glass, looking in particular at one special piece of the glass.
It's special because it has very distinct layers. The layers consist of dense glass, which is almost free of bubbles, and foamy glass, which is full of tiny little bubbles.
Wasson believes the layers were formed by intense heat radiating from above, from an extremely hot sky, and he remembered the explosion over Tunguska.
When the thought came to me that it required a hot sky, I thought immediately of the Tunguska event. That's exactly the kind of event that I need. An aerial burst, but many, many times larger than Tunguska. Perhaps 1,000 times or even more times larger.
And the massive fireball produced on Jupiter by the comet Shoemaker-Levy seemed to offer a possible explanation.
I thought, how nice. The Shoemaker-Levy comet seemed to me to be ideal for producing an aerial burst and producing desert glass.
It set both Wasson and Boslow thinking, could a similar aerial burst happen here on Earth? To take this idea further, Boslow needed to adapt his computer model to simulate an aerial explosion, and for that, he needed more data. He wanted to see for himself how widely the glass was spread in the desert.
I think it's helped a lot to see the distribution of the glass, how widespread it is in some places, how concentrated it is in others.
Scientific papers say the glass is scattered over 6,500 square kilometers of desert.
Well, it's not clear to me whether the current distribution was the actual distribution when the event occurred.
The Sahara only started to become a desert about 7,000 years ago. And during the last 30 million years, there have been big rivers and lakes here.
What I think is that the glass was originally at a much smaller area.
It's hard to believe looking around.
And now it's just sand and nothing but sand. There were lakes here some time ago and there was some water, and it transported the glass farther away from the area where it originated.
Boslow is now confident that 30 million years ago, the distribution of the glass in Egypt was smaller than now, but it still needed a massive event to produce it. He fed the latest data into his computer model.
What we modeled is 120-meter diameter object entering the atmosphere at 20 kilometers per second, and we started off the simulation way above where this frame starts.
To explain the evidence of an actual impact found in the desert, the simulation allows a fragment of the meteorite to reach the ground and make a small crater. But such a small impact would not produce the glass. The simulation also shows something far more powerful is happening at the same time. Before reaching the ground, the incoming meteorite is burning up, leaving a trail of incandescent material in its wake, a massive column of fire which turns into a fireball.
The widest temperature here is the temperature of the surface of the sun. And as it expands, the fireball is actually pinned against the surface, and it's moving very rapidly beyond hurricane force. So we've got this blast of air that's hotter than the melting temperature of the sand blowing across the sand, so it's melting the top surface, and then that melt freezes to form the glass.
And just like when Shoemaker-Levy impacted with Jupiter, an enormous plume of searing gas is streaming out into space.
So while all this material is creating this fireball down on ground level, there's also a plume that's being formed at much higher altitudes, 80 to 100 kilometers above this level, and it's ejecting material out into space.
The simulation shows that even a relatively small 120-meter meteorite can create a fireball hot enough to produce the mass of glass in the Egyptian desert. It's an explosion that makes the first atomic bomb at Trinity look tiny.
And what I want to emphasize is that it's hugely bigger in energy, hugely more powerful than the atomic test at Trinity, 10,000 times more powerful.
Wasson and Boslow now think they've solved the mystery of how the desert glass was formed in the Great Sand Sea. "30 million years ago, an asteroid was on a collision course with Earth, heading for Egypt. As it began to burn up, it created a hot plume in its wake. Before reaching the ground, it exploded into a blistering fireball. Surface temperatures immediately reached 1,800 degrees Celsius. The ground, which was mostly sandstone, melted and was transformed into yellow-green glass. Above the surface, a column of superheated gas propelled itself into space. The total effect was far more devastating than if it had simply hit the ground. The theory predicts that an aerial explosion is much more likely if an object breaks up easily, like the fragile comet Shoemaker-Levy. So how common are fragile objects in space? An encounter in 1997 proved an eye-opener to the scientific community when a NASA spacecraft flew past an asteroid called Matilda. Matilda's slow rotation showed it was not solid, but was a loose assembly of rock held together by gravity. They call it a flying rubble pile.
We've discovered a number of other asteroids which have similarly low densities, and this has led to a real paradigm shift where now it's accepted that most asteroids probably consist of rubble piles and are extremely weak.
These rubble piles are liable to explode if they enter the Earth's atmosphere. Wasson believes that small explosions, like the one over Tunguska, could happen as often as once every 100 years. Larger ones, like the one over Egypt, are less frequent. Wasson has evidence from one other place on Earth of a large aerial burst, this one on a truly cataclysmic scale. He's found pieces of glass throughout Southeast Asia.
They can be recovered from a broad region of Thailand, Vietnam, southern China, and Cambodia. The curious thing about it is no crater has been found.
Wasson believes that about 800,000 years ago, a flying rubble pile broke up whilst on a collision course with Earth. Each fragment created its own fireball.
Within this region, certainly, all the humans would have been killed. There would not be any hope for anything to survive.
Can we protect ourselves from this happening again? The suggestion in recent Hollywood films that a large asteroid heading for Earth should be blown up is possibly not the best idea.
In those movies, yeah, Hollywood certainly got it wrong. You can't just explode an asteroid just before it hits the Earth and suddenly the pieces disappear. Now you have a lot more smaller pieces hitting the Earth and they're all making fireballs. You could actually make it much worse by attempting to explode an asteroid just before it collided with the Earth.
Blowing up the asteroid would have the unfortunate effect of greatly increasing the chance that one of the pieces might explode over a built-up area.
While the probability is small, if it hit in the wrong place, it could be devastating for a city.
In a city like London, the devastation from even a small fireball could extend over an area 8 miles across. Luckily, it could be millions of years before we have to deal with a large asteroid. But the smaller ones will keep coming. And we know now from the explosion in the Egyptian desert just how devastating that can be. And we also know it will happen again.
There are hundreds of times more of